super excited to be here today. I'm gonna be walking you through another exciting topic in statistics. Of course, statistics is like a story, a story that goes on and on and on. Before I get started today, I want to remind you on Friday, we basically gonna give you some information about the midterm two. And of course, you don't even need what you did in midterm one or what you did prior to midterm one. The only thing that you actually need to focus on is the assignment solution. And of course, the areas that the midterm two will basically be extracted is going to be, I told you the other time, the weighted least square is going to be number one, and number two is going to be bootstrapping. Number three is transformation. Number four is analysis of variance test. You remember when we were comparing models, right? And number five is going to be general linear hypothesis. So those are the five areas, the midterm two is actually going to come from. Okay, so once again, I want to welcome you to my lecture today. On Monday, we started what we call variable selection. Okay, the idea behind variable selection, the force behind variable selection is actually the desire for parsimonious regression model. Okay, so when I say parsimonious, so when I say parsimonious regression model, we basically need, regression model with few numbers of predators. We don't want so many predators because when we have so many predators, we basically there's going to be problem. Okay, maybe problem of multicollinearity. Okay, and so on, like that. And let me tell you this: another reason why we need few numbers of predator is because of the fact that some unimportant variables in the model will mask the effects. We not make the significant one to be significant. We not make the important one to be significant at the end of the day. I don't know whether you know what they call masking effect. Situation where you tolerate irrelevant predator variables in your model. The irrelevant predator may force, okay, the important one, okay, to be less significant. In fact, not to be significant at all. And that is the reason why we need the idea of variable selection. And of course, another reason why we need variable selection is just to improve on the model. Like, what do we want to improve on? To have a greater accuracy in precision. Okay? And that's exactly. So in today's, we're going to start by trying to improve on the ordinary least square. The ordinary least square is just the conventional approach that we use on linear regression. If everything work okay, if the assumption hold, if there's no problem at all, then I'm going to also walk you through what we call the bias and the variance, because if there's a problem in a model, it's going to affect the bias, also going to affect the variance. Then from there, we're basically going to go into the shrinkage approach, that we call the LASSO and the ridge regularization, which is more or less like something that can rescue us from overfeeding. Okay. Now, the most important thing that we basically want to see here is how can we improve on the ordinary least square. Number one way to improve on the ordinary least square is to go by way of subset selection. What I walk you through on Monday, what do I mean by subset selection? The subset selection is more or less like, oh, I got so many predators in a regression model. And I'm only going to use the subset of those predators, those ones that I know that they're basically going to contribute significantly to the response. And how am I going to do that? I propose two methods of doing that. Number one method of doing that is when we consider all subset selection. Of course, you want to figure out a particular subset within a sample space of subsets. When I say sample space of subset, we have so many possibilities of subset. And by all subset selection, you know how it works. For instance, if I'm working with a model with 4 predators, you know what I'm going to do? The off subset selection will basically figure out the best 1 predator, the best 2 predator, the best 3 predator, the best 4 predator. Okay, and at the end of the day, it's going to use a matrix of evaluation that takes into consideration the model fitness and model complexity like AIC, BIC, or adjusted R square to decide on which one is the best out of that. That is what we call the up-subset selection. But let me tell you something, experience has shown that the up-subset selection as well could miss the best model. Another approach in the subset selection is what we call a stepwise regression that I walk you through on Monday. The stepwise regression, we have what we call the forward, we have the backward. We also have the one that proceed in both ways that we have not done in this class, and we're going to do that next week. Okay. Of course, what the forward selection does, the forward selection is going to start from the intercept. Oh, I'm going to start with a model without predator at all. And I'm actually going to be going like adding the significant one using a criteria that could be AIC or BIC. You get what I mean? I demonstrated that to you on Monday. And of course, the backward elimination is going to start with a complicated model. Having all predators, and what is basically going to be doing is going to be going backward, removing the insignificant predator. But let me tell you, we identify one issue with one of the stepwise regression the other time. When I was demonstrating that to you, there's one of them that actually skipped the best model. And let me also tell you this. When the number of predators is more than the numbers of observation, I'm going to write that. When P is greater than N. Okay? When P is greater than N, which means the numbers of predators is greater than the number of observation, backward elimination is not visible at all. Don't consider it at all. Please take note of that. It has been mathematically proved and statistically observed that when the number of predators is more than the numbers of observation, don't consider backward elimination. It's not going to do a great job. Okay, now another criticism of the stepwise method that we did on Monday is that there could be conflict. There could be conflict in terms of how we select the best model, in terms of should we use forward elimination with AIC, or should we use forward elimination with BIC, or should we use forward elimination with the adjusted R squared, and stuff like that. There could be conflict. And that is another criticism. Now let me tell you what we do in statistical analysis. Before we can have a way to improve on a particular technique, then it means we've already identified the weakness of that particular technique. And that is the reason why we normally want to consider a brand new technique. But that doesn't mean a brand new technique will not also have its own limitation. Okay, now let me tell you this. The way out of the success selection now is to go for the shrinkage. That we want to do today. When I talk about shrinkage, what we're basically going to do in shrinkage is just like we're actually going to introduce something that we call a regularization parameter that will shrink the coefficients of unimportant predator to zero. Okay? Can we have a way? Let me tell you this. We can actually have a situation where this is more than this. An example is a microarray analysis. Microarray analysis. You can talk about environmental study. Environmental studies. You can actually talk about financial analysis. Maybe you actually want to talk about detecting fraud. Okay? A particular bank is trying to detect fraud or want to figure out whether the customer is going to default or not. There's basically going to be a lot of predator. Credit history, the gender, so on like that. It could be more than the number of customers itself. Okay, so the idea of shrinkage is basically going to work. We also have another idea, dimensionality reduction, that we call the principal component analysis. That will solve the problem of multicollinearity, but the issue is just that we're no longer going to be working with the original predator. We're just going to be working with a principal component. Then the interpretation is become an issue. Now, I told you the other time, when there's a problem, it affects variance, it affects bias. Now, the question now is, what do I actually mean by bias? What do we mean by variance? You know, the bias is just the difference between the average prediction and the true value. I'm going to say that again. The difference between average prediction. Where is the average prediction coming from? From our model, right? It's coming from our model, right? And the true value. This is the true value. This is the true value. This is the average prediction. Expected value of that. This is an average. The difference between them is what we call bias. Does that make sense? And what do we mean by variance? Then by variance, we're talking about the variability of model prediction for a given data. The variability of model prediction for a given data. That's what we mean by variance. But let me tell you this. When the number of observation is less than the numbers of predator, that is, if I have this situation works for OLS. The OLS, if all assumptions are not violated, the OLS will be called a balanced model. The OLS will be called a balanced model. Oh my God. A balanced model is the one that have a low variance and low bias. Does that make sense now? That's what we call a balanced model. It has low variance, low bias. Now take a look at what I'm showing on the board now. I mean, you know what I'm projecting now. This is the situation of low. This is what we want. This is a balanced model. Low bias, low variance. But this may be difficult to get. Okay? Now, this guy now, high variance, low bias. We normally have the issue of high variance in a situation where you pay more attention to the training data. I'm going to say that again. when you pay more attention to the training data, then when you pay more attention to the training data, then your model will not perform great on the test data. Paying more attention to the training data means, in a way, your model will capture noise when you try to capture everything. This is it. Paying attention to the training data. More attention to the training data. Now, high bias, low variance here, you pay little attention to the training data. You oversimplify. I'm going to say that again. You oversimplify. This will result to the error. You're going to have huge error on the training performance, and not only that, on the test performance. Oh my God, this is a double tragedy. High bias and high variance. This is not good at all. Okay. Now, I'm just trying to show you how that is actually play out. But let me tell you this. Like I said, when the number of observation is greater than the numbers of predictor, of course, we expect the OLS to be balanced model. And in a situation where the number of observation is not much more or larger than the numbers of predictor, then we're actually going to have what I call over-parameterization. Oh my God. When I say over-parameterization, means I got a lot of parameters in my model because I got a lot of features in my model. I'm actually going to write that now. Over-parameterize. And you know what? The over-parameterization will lead to bias, bias parameter estimate. This is a situation where the number of observation is not much larger than the numbers of predictors. But let me tell you this. Situation where the numbers of predictor is now more than the numbers of observation, you know what is going to happen? In fact, you may not be able to estimate your parameter. I'm going to demonstrate that to you now using the OLS. I'm going to say that again. Situation where the number of predictor is basically more than the number of observation. Okay, then what is going to happen? The OLS will be impossible. I'm going to show you that now. We have y equal to this, right? This is our multiple linear regression model. What is the result? Finding this, that will give us the beta 1, the beta 2, up to the beta p, right? But let me tell you this. Situation where P is greater than N, okay, this guy is going to break down. OLS we break down. How? We're going to see now. If I want to get this guy here, I need a design matrix X prime X, right? I need to get the inverse of that. And to get the inverse, in mathematics, the inverse is the adjunct of cofactor, this, divided by the determinant of X prime X. And let me tell you this. Situation where P is greater than N, this guy will be singular. Do you know the meaning of singular? When the determinant of X prime X equal to 0. That is the meaning. When the denominator of a fraction is 0, what will happen? The fraction will be undefined. And undefined means there's no way to get this guy. If there's no way to get this guy, there's no way to get this guy. And that actually occurs when P is greater than N. Because when P is greater than N, the number of the degree of freedom will reduce. Don't forget, if one, the degree of freedom used to be N minus P, right? When the P is greater than N, the numbers of degree of freedom will goes down. Then if it goes down, what will happen to the variance? The variance will be going towards infinity, indeterminate. Okay? I wanted to take note of that. Now, what are the problems when P is large? Of course, there's going to be unnecessary complexity. You know what causes unnecessary complexity? Because you have some irrelevant variables in your model. That's why you have unnecessary complexity. And not only that, the unimportant variables that you have will affect the important one. It will make the important one not to be significant. And the last one, the last problem of multicollinearity. That is going to arrive. Take note of that. Okay, that is what I'm. So this is the what I'm showing you now, just to let you know the meaning of low bias, high bias, and stuff like that. Now, what is the solution? What is the way out when P is greater than N? Oh, the way out is regularization. Let us go by the way of LASSO and Rage. There's something that surprised me in this world. Anytime there's a problem, solution will always arrive. The solution may not arrive at time, but I know the solution is going to come. Human beings have the capability to look out for solution. So the regularization is one of the ways to improve, our model to work on seeing data. Let me tell you something. Your model could perform well on the data you see, but may not perform well on seeing data, which means you cannot generalize. Your model will only perform well within the data you're seeing now. You did not actually put on that model just for you to explain variation in the data that you are seeing only. You also want to use the model to generalize on the data you have not seen. And that's why I told you the other time, we have a basic science that understand, where we try to understand the world, and we have an applied science where we actually need to make a prediction. And you know what? The regularization minimizes the validation loss and trying to improve the accuracy of the model. Okay? It will avoid overfitting, by adding a penalty to the model. Okay? With high variance and thereby shrinking it, it's going to add a penalty. What do you think you actually want to do? You want to reduce the variance. The variance is too high. And it's going to add a penalty to reduce the variance. But, oh my God, when it's reducing the variance, it's going to increase the bias. That is the issue we have. And you know what? That we're okay. We're fine. We are okay. And that is the reason why what we need to do, we need to optimally obtain the values of that turning parameter in such a way that it will help us in a way. There's going to be a trade-off between the bias and the variance. Okay, I think I put some stuff. Okay, go ahead.
Validation loss the error in this situation?
Would be what?
Is validation loss the error in this situation?
Exactly. The validation loss, that is the error. Exactly. You are right. Okay, now take a look at this. And that was why I said it reduces variance. It will help us in shrinking the unimportant variable, because our intention is to eliminate the unimportant variables. When they are in our model, they will cause problem. Then they need to be eliminated. Okay? The approach of regularization will help us to reduce variance, but it's going to increase bias. Okay, and the two main regression method that actually do that is what we call the lasso and the ridge. So there are two types of regularization. Okay, the lasso is called L1, the ridge is called L2. Take a look at them. Okay, so this we want to regularize. Okay, I want to go, the material for today. I know we're not going to finish it today. We're going to finish it on Wednesday. Wait a minute. Okay, I'm going to see. Next week, you see, what is it Thanksgiving?
Thursday.
Thursday, right? Okay, if it is Thursday, uh, what I'm going to do on Wednesday, uh, okay, you know what? I'm gonna send a message because I also want students to enjoy the Thanksgiving. Since Wednesday precede the Thanksgiving, I'm gonna have my lecture on Zoom. So anywhere you are, you can attend the lecture on Zoom. You like that, right? Okay. Okay. Now let's go to the number one on the regularization that we call the ridge regression. Now, the idea behind the ridge regression. Now, take a look at this guy. This is the sum of square regression, right? I mean, this is sum of square error, right? Okay, from the OLS. But what we do in the ridge regression now is to add a parameter term, lambda. Okay, and when lambda equal to 0, where are we? We are back at the OLS. Lambda equal to 0 means, there is no variable that is not important. All of them are important. When lambda is going towards infinity, you know what that means? There's a lot of unimportant variables that we need to shrink. Does that make sense? Now, let me tell you this. Ole and Kenner, 1970. Actually, I'm going to explain this to you now. Okay, that was a scientist, statistician called okay, and Kennard in 1970 in an attempt to solve the problem here when the P is greater than N. And these two guys said, this is what we can do. They noticed that when they had small value to X, it will change, drastically. There's going to be it caused a large difference in this. And you know what they did? They decided to add what I call, instead of using this guy, they decided to add lambda high. This is lambda. High is identity, which means I'm talking about the diagonal, right? They added something to the diagonal of this, right? Then after adding this to the diagonal of this, and they decided now to take the inverse, before they multiply by this, they have a new beta that we call ridge. And this guy performed better than this guy when this problem exists. I'm going to say that again. Hole and Kennard did that in 1970. They added, depending on the dimension of this matrix, if it is 2 by 2, okay, they're going to add, if it is 2 by 2, they added something here and here. Because the lambda high, don't forget, lambda is basically 1001. You understand that, right? Which is basically going to be lambda 0, 0 lambda. So they had, so which means this and this is being added at, that's before they find the inverse, and they realize when they did that, that solved the problem. But the fact remains, what do they need to add? What is the constant? They need to add the lambda, need to be optimally determined from the data. Does that make sense, right? Because they will be able to solve the problem when they actually use the correct, lambda. Okay, and that's exactly what we're doing here. Adding the lambda to that. When lambda is greater, we expect the lambda to be greater than 0. It's going to be a turning parameter. The larger the lambda, the more shrinkage. I told you, the larger the lambda, the more shrinkage actually means more unimportant variable that need to be shrinked towards 0. Does that make sense? Okay. Let me now tell you, this is going to take us into mathematics of optimization. I don't know whether has anybody heard about Lagrange optimization. Okay, so the Lagrange optimization is going to, because minimizing this now is going to be subject to a particular constraint. Okay, so, and of course we'll be able to find that. Okay, now the OLS estimates are unbiased if the model is true, but the variance can be high. That is the reason why we come here. And of course, when you have a lot of predator, they're going to be correlated, right? And they're basically going to cause problem. And the penalty that we had to solve the problem, we increase the bias, but it will reduce the variance. Does that make sense? And that is the reason, last thing here I said, they need to choose a tuning parameter carefully to achieve the right bias variance trade-off. Okay, you need an approach to be able to use the right tuning parameter lambda. Okay, so I wanted to take note of that. This is what I was talking about the other time, the computation of regression. This is for the Okay, want to ask a question? Go ahead.
This one, so lambda is a matrix or a scalar, because in the slides also it's not lambda I. So it's just a single value, or do we have different lambdas for different coefficients?
That's a very good question. You are trying to say it's a constant. Look at that. When you have a value out, it's the same value. When you use a constant to multiply a matrix, it's the same thing you are adding. That's a good question. If you have 4 by 4, right? 4 by 4, if the dimension of S prime S is 4 by 4, right? Then it is the same value of lambda that will be added to the diagonal. You've asked a good question. That's why we call it a constant value, lambda. Does that make sense? Okay, now look at it here. If we only use this guy here if there's no problem, but and the problem that we normally have is when the numbers of predator is more than the number of observation. Let me tell you, when the number of observation is much more than the numbers of predator, of course we can use variable selection method that we've been using, like all subsets, stepwise regression, the ANOVA test that you generally have. There's no problem with that. But the problem comes when this guy is greater than that. When this guy is greater than that, of course, the only thing that is going to work is shrinkage. Let me tell you what we're doing now. It is not only statistics we're doing at the moment. We're also doing machine learning. It's an agreement. Does that make sense? We're doing machine learning now. And this happens in big data. Big data. Does that make sense? This is the same approach. Now, I'm going to tell you the difference between LASSO and the ridge regression. The ridge regression will not shrink unimportant variable to 0, but it will still return them in a model, but only that they will not be significant. I'm going to say that again. The ridge regression will not shrink the parameter, the regression coefficient to 0. We're still going to have them in the model, except that they will not be significant. Okay, and because of that, that is the disadvantage of ridge regression, which means the ridge regression is not even doing what we ask it to do, in terms of completely eliminating the unimportant variable. It still retain them, except that they are in the model, but they're not going to be significant. I wanted to take note of that and let me also, the ridge regression helps us to solve the problem of multicollinearity. Okay? So I just wanted to take note of that. But the penalty that we use in ridge regression is not enough to force the unimportant one to 0. Okay? He only did the job of making them not significant, but we still have them in our model, which means, and that is the reason why we need LASSO. there's something I want you to pay attention to now. The lasso will solve that problem. It will completely eliminate the insignificant ones. We're not going to see them at all. You know why? Let us now compare the two model. Here, we consider the square, but here we consider the absolute value. Look at that. And that is the reason why the penalty in the two regularization, okay, is behaving differently. Okay, do I need to square or do I need to take an absolute value? But when I take the absolute value, the penalty with the absolute value, which is for the lasso, did a very, very great job of completely eliminating the insignificant predator from the model. Okay, so that's what I want you to see. Now, in case you don't know, we call the L1 lasso, we call the L2 range. And the difference is just that one is the absolute, the sum of the absolute, and the other one is the sum of the square. Now, okay, so this is another thing I wanted to see. Increasing the lambda. You know, at times you may want to, maybe you have some values of lambda, and that's okay. When lambda equal to 0.5, what happened? When lambda equal to 1, when it's equal to 2, maybe you are just assuming, right? Now, increasing the lambda will increase your bias, but will reduce the variance. We don't want to continue like that, increasing the lambda because we want to reduce variance. Don't forget you are creating another problem. Now we should have a point where we're going to stop. An optimal value of the lambda that will do a great job for reducing the variance at the same time taking care of bias. That's exactly what we need. And don't forget, when lambda equal to, when you take a look at this, smaller lambda corresponds to higher module complexity. You know the meaning? Smaller lambda means it is, you know, the one you shrink, the omnipotent variable we shrink is not much. Okay? And when lambda equal to 0, let me tell you this. When you don't introduce penalty at all, there's no bias. That's why we say the OLS is unbiased. The problem with the OLS is what? High variance. But when lambda equal to infinity, when lambda is going to infinity, no variance, but be careful, no variance will come with the high bias. How do we stand in the middle? Okay, and the question now here, can we say whether Ridge or Lasso is better? Then I'm going to tell you this, Lasso is better. Okay, Lasso is better. Okay, now, prediction versus interpretability. I've mentioned that in this class. Okay, the larger lambda means more coefficient set to 0. Okay, but frequently better prediction is achieved with a smaller lambda. Take note of that. Okay, with a smaller lambda, okay, better prediction is achieved. I will quickly go to, then we also have further improvement that you don't necessarily, because at times, when Lasso, you know, Lasso also has its own issue, but not much. But we can, you know, some researchers are considering combining the two, where they're going to have two penalties. Take a look at that. That's what we call elastic regression. But you don't need to, that is higher. You know, maybe by the time you come back again, if you want to take statistics again, you know, you can take a look at the elastic, where we're actually going to have, in that, somebody asked a question the other time, right? When you say, when I have a different values of lambda or different value, that is here, right? Look at that. The lambda here maybe is going to be different from that, but in this case, you are looking at the elastic net. Elastic net is also doing a great job. Okay, now let me quickly go to, now I added this today. If we want to know the truth, if we really want to compare Reach and Lasso, you know what we're going to do? We need to first start from the truth. Like, we have to know the truth. When we know the truth, then the next thing we're going to do, we're going to use Lasso and Reach and see whether any of them will predate the truth. You get what I mean? Because of that, I want to go into simulation. Okay? I want to go into simulation where I have how many predator? And I already know their true values of beta. Look at that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I mean 10. And I already know that the 4 here, they are insignificant because their beta is 0. Somebody asked a question here the other time in this class that when beta equal to 0, when the magnitude equal to 0, of course, it means you don't even need to include that in the model. Now, you know what I want to do now? And I want to perform a ridge regression. But here, I'm assuming lambda equal to 0.1. We have a way to determine lambda. Now, when I do that, on the same data, I perform linear regression using OLS. These are my true values. The ridge regression give us this. The OLS give us this. Oh my God, the OLS values are far from the true value. But look at the ridge regression in a way, very close. I told you the other time, when you look at the p-value associated with these ones, I know they will not be significant, but they are still in the model. But when we now decide to go by the way of LASSO, look at it, I wrote the code. Let us see now. LASSO, where are you, LASSO? Oh my God, see. So which one do you prefer? That should be LASSO. Because, take a look at this. If I come to you to seek for an advice, if I want you to tell me what I'm going to eat tomorrow, maybe I don't know what I'm going to eat tomorrow, but I know what I ate yesterday. Before I'm going to ask you to tell me what I'm going to eat tomorrow, I'm going to say, can you tell me what I ate yesterday? If you tell me exactly what I ate yesterday, whatever you're going to tell me about tomorrow, I will rely on you. Because you've already told me what I ate yesterday. That is the reason why, in statistical analysis at times, if you really want to know whether a particular module perform, what you basically need to do is just like, okay, let us have some true values, and let us measure the deviation of, the whatever the model we're proposing give, okay, with the true value. That's what we're doing here. So take a look at that. Okay, and I applied this to real life data, and it's a data on unemployment. Of course, everybody knows, unemployment is a critical socio-economic and political concern of any country. Okay, that's why in the United States, when the president, I think in the last month, when maybe around 200 and something thousand jobs, they're going to celebrate. Okay, when you're actually getting, generating more jobs, of course, the unemployment rate is basically going to be going down. Now, if we have some factors, it is not necessary that when it is only, we don't, it is not until the numbers of features is greater than the number of observation that we can use shrinkage. We can also use shrinkage even because here now we are only considering maybe four predator on this. We can still use that. You get what I mean? Only that they're going to perform so great when the numbers of features, the numbers of predator is greater than the numbers of observation. Now you want to have access to that data, we load all these packages. And of course, we want to do it the way they do it in machine learning, because we have an agreement now in statistics and machine learning. What we're going to do is, here we are setting a seed. We want to have the same data. We want to split our data into two. Don't forget, the other time I said a particular module could behave well on the training data, but may behave poorly on the unseen data. And what we now do in statistics nowadays, and also what they do in machine learning, is to split your entire data set into two. But make sure the significant parts of the data is committed to training. Now, I'm actually, 0.7 here, I mean, I actually want to use 70% of the entire data set for the training and 30% for the test. Okay, some people could do 80% to 20, but just make sure the significant part of the data is committed to training. Okay, now here, this is just a code for all of that. Now, the very first thing I did with fitted linear regression, OLS, this is the result. Now, let me tell you this. If you take a look at the OLS, everything is fine. If you take a look at all this, but I said, don't touch this at times. Okay, what you see here, it is the result of the training, not for the test. You get this result when you use how many? 70% of the data. Okay, we don't want a situation whereby it's going to perform so great on the training and not perform great on the test. We don't want that. We want the situation where it will perform well here. It is also perform well on the unseen data. The unseen data here is the test. Okay, now take a look at this now. Okay, and we normally use two metric of measurement here when you split your data. We use what we call the root mean square error, and we use adjusted R squared. Okay, now you know what we have done here? We computed the mean square error and the adjusted R squared for both the training and the test. Take a look at that. The mean square error and the adjusted for both training and the test. And that was why we have that values, and that is what I interpreted here. Okay? Look at that. Okay? The lower root mean square error, the model that have the lower root mean square error is a very good model, and the one that have the high adjusted R squared. So now when you take a look at the result that I actually presented here, I presented the one for the both training and the test. Okay. Now this one now is for the linear regression. Without going to the regularization, we split it again. We use ridge regression. In the ridge regression, we did not suggest the value of a lambda. We want to determine the values of a lambda optimally. Okay? But there's something that we call alpha. For ridge regression, alpha will be 0. For LASSO, alpha will be 1. Good job. Good job. Send a message to me for extra credit. Yeah, because I think you're really following that. Keep track of your extra credits. Okay, now, in the end, we get the optimal values of lambda that we're going to use for the ridge. And we now fit it on the data. Okay, we write the code for all that. We fitted that. This is the result for ridge regression now. The root mean square error, this and this is for the training, and this is for the test. Now, if you take a look at this, very close, okay, it performed more better on the, on the training, but still very close. But if you take a look at this, it performed better on the test. Looking at the R square, look at that, right? That is the explanation, right? That is for the ridge, right? Then we do the same for LASSO. Okay, we did that, and we also have that. Take a look at that. That's an improvement. Oh, what we're going to do next? On Friday, we're going to do revision, the midterm 2, practice. Is there any question to ask? There's a lot of stories in statistics.
In the simulation, why did we take n to be 100 and p to be 10 when we are trying to get a situation in which p is greater than n?
Why do we take n to be where? When I get there, tell me.
In the first example.
In the first example.
Simulation that we've done.
Oh, okay. I'm going to go back to that simulation now.
Yeah, this one. Yes.
Oh, yeah.
Yeah.
Yeah, right?
N is 500 and p is 10.
Yeah, you know, what I've done here, this is for situation where p is less than that. We can do the same. I want you to do something today. Follow this code and do the opposite. Yeah. But when you are doing the opposite, we have a way to repeat. Yeah, you can do that. Yeah, good. That's a good question. Send me a message for extra credit for that good question, Okay, that's why I'm going to stop today. Make sure you stay safe and have a lovely day. See you on Friday.